Hi everyone, I'm Pierre. It's my pleasure to be here. I'm a grad student in the group of Simoncelli at NYU, and I work also across the street at the Center for Computational Neuroscience. And today I'll be telling you about self-supervised learning, more specifically about the neural representations for predictive processing of dynamical visual signals. So let me start with a broad normative statement. And that is that we're extremely good at making accurate predictions, and we have to learn to adapt those predictions to our environment. In doing so supposes that we have some amount of understanding of the signals we're predicting over. And we can think of simple predictions made by, for example, simple cell organism. Think of bacterial chemotaxis, so you're following a chemical gradient and trying to go to a food source. Or more complex predictions that involve internal variables, even planning and memories, like when you had to choose a major for college. So together, these ideas have the potential to offer an organizing principle to think about brain function and also machine learning. So this is a broad space where a lot of interesting work has been done. On the one end, there is the mathematical theory of information bottleneck. So that's the work of Tishby and Bialik. It's very beautiful work. And the challenge here is to estimate mutual information on data. So it's hard to relate those computation to neurobiology. On the other end, there is the fully engineered solution of convolutional LSTMs. So here, the group of Bill Loader and collaborators trained elaborate neural networks to predict upcoming frames in videos. And these obtained really interesting results, but the architecture was a little bit ad hoc. So it's, again, hard to relate that to the neurobiology. So I'm going to aim for something intermediate at a medium level of abstraction and think of modeling populations of neurons by being constrained at the same time by the function being performed. So let's look specifically at the visual example. So here is a bicycle carrier navigating through Midtown. And this is meant to illustrate the critical importance of prediction, okay? You really have to know what other agents in your surrounding are doing in order to navigate successfully. And what you get are all these light intensity measurements in your retina, because for now I'm going to focus on vision. So how do we make sense of this maelstrom of information? So here is what this looks like in the state space of pixels. So each axis is the intensity of one pixel in the video. And as the video plays, we trace a trajectory that's extremely curvy in this state space. And the question that I want to ask is, how does our visual system transform this information into a space where prediction is enabled? So specifically here, if you were going to do prediction by linearly extrapolating the trajectory of previously seen frames, the prediction would be very poor and land far away from the actual next frame. So an idea in the field is to say, well, a good representation would be a representation that linearizes those dynamics. Right? So these are ideas that go back at least to the 90s in the work of Peter Foldiak, and there's a series of interesting work along this direction in computational neuroscience. And let me start by going back to a very fundamental difficulty. All right, so here is the simplest situation we could imagine. This is a one-dimensional signal. It's a superposition of two sinusoids. And as time goes by, it shifts in space. So the x-axis is location in space, and the y-axis is intensity. So again, if I visualize this signal as tracing a trajectory in pixel state space, and only show you the first three PCs, it looks like this potato chip. So it's very curvy, and if I linearly extrapolate such a signal, so I use a linear method, I'm going to land far off of the observed next signal. But here there's hope. This is a structured signal, and we remember that in the Fourier space, translation is simplified. Right? So let's look at the Fourier coefficient of this signal. Again, I'm using the same color code, so red, green, and blue correspond to the three successive time steps. Here you have frequency on the x-axis and the real and imaginary component of these coefficients. And as the signal shifts, the amplitude of each of these two components, this is a superposition of two sinusoids, the amplitude is fixed and the phase cycles at a rate that's proportional to the frequency. So this was a linear transformation. We haven't changed anything about the curvature of the signal. But in this space, we can pair together the real and imaginary part and do a coordinate change, go and look at the polar coordinates. In those coordinates, now the transformation is completely linearized. Right? The phases advance linearly, and the amplitudes are static. So I'm only showing you one amplitude and two phases. But in this space, prediction is enabled. So how do we find such spaces? And more importantly, do these spaces generalize? And turns out, yes, this is a very general property. It's a beautiful property. And any Lie group that's commutative can be diagonalized in this way. So here, a precise way to say what's happening is that the complex exponentials are the eigenvectors of the translation operator. But other operators, rotation, for example, can be diagonalized as well. So this was a base case with a simple one-dimensional signal. Really, we're interested in real video. So here's an example of a camel walking across the scene. Again, same thing. I'm going to show you the trajectory in state space. These are the first 3 PCs. It's a very curvy trajectory. This trajectory actually is closer to being 7-dimensional, and I'm only showing you the first 3 dimensions. So here, there's a challenge. The global transformation of the Fourier transform doesn't apply. Different locations in the image move in different directions. So we really need local processing. Moreover, there are like small things, like the legs moving, or bigger things, like the hump moving. So there are different scales of objects moving. So I'm going to use a multi-scale oriented representation, very much like what Bruno told you about earlier. So specifically in this case, it's also a wavelet decomposition. It's also a complex valued wavelet decomposition. I'm using, in particular, the steerable pyramid. So it looks like this. Here's an example with 4 different orientations. So this would be the parameter theta from earlier in the day, and 4 scales. So that's the parameter j that Bruno told you about. So these are the example basis vectors. So they correspond to they are the generalization of the sinusoid of the Fourier transform. And these are the odd symmetric ones. And for each of these channels, I also have corresponding even symmetric filters. Together, they form a quadratic pair. They are Hilbert transform of one another. So now what I'm going to do is I'm going to project this video along these directions. So I'm going to plot 2D projection at each scale and each orientation along the even and the odd symmetric filters and see how the trajectory evolve. And again, we see that these trajectories actually do have some amount of structure. Some of these trajectories follow a circular trajectory like previously in the Fourier example. So again, using the polar coordinate transformation, we can look at the trajectory in that space after the nonlinearity and see that we've partially linearized the whole image. So this was at one location in the center of the image, and I'm just going to concatenate all of these coefficients at every location and show that together we've enabled prediction. So now the first PC explains about 80% of the variance. Okay, so here we built in a transformation, the steerable pyramid, and I started by telling you that we wanted to discover such symmetries from data and maybe even more general ones. So I'm going to cast this problem as a learning problem, a self-supervised representation learning problem. So this goes as follows. You have the time axis at the bottom here, and let's say we've observed the current frame, t, and we remember the previous one, t minus 1. We're going to represent these signals using a parameterized mapping f with parameters w, and we are going to obtain maps of coefficients. So let's think of this as a convolutional operator. So at every location in space, we'll get coefficients. And if we pair the channels 2 by 2, we'll get corresponding coefficients that we will interpret as the real and imaginary part of a representation. Okay? So at every location here, we get 2 coefficients. We can think of them as little complex numbers. And the prediction here, PW, for now, I'm not going to parameterize it. I'm just going to reuse the same idea as we observed in the Fourier case and the steerable pyramid case. We're just going to continue along these circular trajectories. So I'm going to assume that the amplitude doesn't change and that the velocity that exists between t minus 1 and t can be applied again between t and t plus 1. So that is, I'm assuming there is no acceleration for simplicity. That's how I come up with a prediction for this coefficient. I do that at every location for every pair of channel, and then I have another parameterized mapping that goes back to the signal domain, where I can compare my prediction against a true next frame. So specifically, let me say that again more precisely. So for now, consider a linear representation. So we have a convolutional filter W that's applied at every location. So I'm dropping the positional index for clarity, but think of x as a function of both time and position, so your coefficients y also are a function of position. Then you pair them up and get complex activations. To predict the next coefficient, we're just going to advance the phase of the current representation. So z is your current coefficient, and you multiply it by this little unit vector that's going to rotate the phase. The way to see that is that these are complex numbers. They are divided by their norm, so they're unit vectors on the unit circle. And the bar above here means complex conjugation. So we're negating the phase, and multiplying those two takes a phase difference. So that's what does the prediction step. Then, once you have this prediction, you can reuse the same filters on the way back, use their transpose, and get back to the pixel domain. And then we're going to learn those parameters, the weights W, by minimizing the prediction error against the next observed frame with gradient descent. So really the important step was the phase advance that I highlight here. And notice that previously I motivated this idea by taking an explicit polar coordinate transform of my coefficients. Here I'm doing it all in one step. I'm only using the coefficients. I'm not computing arctangents. So that way I can get the benefit of linearizing in the space of phases without having to commit to that circular variable that can be very unstable. So let's verify that this does something reasonable with synthetic data. So for the first case, we're looking at translating sequences. So these are patches of real images. And the group that's acting on these are just translations. So taking a patch, and I'm going in a random direction at a random speed. And I'm going to train the architecture of the previous slide here. And now I'm going to show you the weights that are learned, and I'm going to show you them animated. So these are the weights that we recovered. They're exactly the plane waves. So we've relearned the Fourier transform in 2D. All right, so again, they come in pairs. There is an even symmetric and an odd symmetric, so you could animate them by just applying this little phaser to them. That's what I do to display them as short snippets. If we now do the same thing with rotation sequences, so these are also image patches that are rotating at different speeds in different directions, then we recover what is known as disk harmonics. So they are the exact analog of the Fourier waves, but for rotations in 2D. So that's just to verify that this approach can help us discover symmetries from just observational data. So for now, the methods that I've shown you have a limited expressivity. They only work for the commutative groups, the smooth groups. But we can try and extend and see how far this idea go by considering the performance on real data. So here's an example of a few snippets from a computer vision data set that I'm using to train this exact same architecture. And here are the filters that it recovers. So they come out as pairs. So together, they're selective for a particular orientation at a particular spatial frequency, and they come in groups of two, as expected. And they cover the frequency domain in a reasonable way. So if I fit little Gabor wavelets to it and drop them in the frequency domain, they tile this space in a reasonable way. So this is interesting. It's kind of reminiscent of the selectivity of cells that's observed in early visual areas of primates. Now let me tell you a bit more about the prediction mechanism. So far I've used polar prediction, so that was a fixed transformation. Now I'm also going to aim to learn how to predict. Right? So I was learning the latent space and fixing the prediction mechanism, but as I told you, it's really just a quadratic. So I rewrite the phase advance mechanism of the previous slide using only real numbers this time, so I explicitly write the real and imaginary part as little 2 vectors. And the phase advance delta of earlier, I can think of it as a 2x2 rotation matrix. So these numbers can be computed with several simple steps. First of all, think of the coefficients y's, they're the linear activations. They can be normalized, so that's the first step for the prediction. And the second one is to just expand the cosine of a difference. And this is a simple trigonometric identity. You find that they're quadratics. It's the product of the cosines minus the product of the sines. And typically, products of activations, they are not playing so nicely with the rest of the toolkit of machine learning. People think about pointwise activation functions. So I'm going to rewrite this multiplication as a cascade of a linear, a quadratic, and another linear operation. So that's called the polarization identity. Any product AB can be computed using this little trick by first taking a linear function of your input, squaring them, and then taking a linear combination of those. So what's interesting about this is in neuroscience, it recovers well-known models. So now we've sort of derived them from first principles. The first one is the normalized simple cells that goes back to the work of David Heeger in the 90s, and the direction selective complex cells that are also a key model to understand processing of motion. So these are special cases of our model, and they're now part of this bigger family where we don't have to restrict ourselves to pair of coefficients, the real part and the imaginary part. This was convenient because it matches our intuition of the Fourier transform, but we can relax this and consider groups of coefficients that evolve along predictable trajectories in the latent space. So here I'm rewriting in a diagram what's above. So the first step, these are the coefficients y at different time points that we observe. First, we're going to normalize them, and then they go through this cascade of a linear operation, squaring, and linear operations before producing the next coefficient by applying this little matrix. So here we can learn this coefficient in the gray boxes and bring everything together, learn both the representation and the prediction mechanism. And the idea here is that now we're in the position to handle groups that are more general than just the commutative Lie groups. So let me just show how that works in practice on like an example from the test set. These are 3 frames from a video in the test set. We observed x at t-1 and x at t+1 at time t, and we want to predict the next one. Here's a baseline. So if you were only using the current frame as a prediction for the next one, that's the error that you would incur. And the common way to quantify the quality of a prediction is the peak signal to noise ratio. It's not too high. Okay, so here is a very common approach. So in engineering, people use what's called motion compensation. That's the basis of all the video codecs that we use every day. That's what enables video streaming. So the idea here is to like find in the previous image patches that match the one that you're currently trying to communicate to the decoder. And instead of sending all the pixels, just send the displacement vector so the decoder can copy paste that content. So that's very effective in making smaller video files. Okay, so that's a little bit better than the naive copying prediction. Then using the steerable pyramid, as I showed you earlier, is slightly more performant. And here is the learned version, the polar predictor with the learned filters that I showed as well. We get slightly finer prediction by adding the prediction mechanism in the latent space. Just want to compare all of those to what you would do with a regular CNN. So here is a completely different approach where you just train a cascade of convolutions and rectification to take 2 consecutive frames and predict the upcoming one. Such a network has about 20 stages, so exactly 20 stages, 20 nonlinearities, while what I'm comparing it to is 1 stage, 1 nonlinearity. And it performs just as well. So these trends hold throughout my attempts with various data sets. The CNN has a tendency to overfit a little bit, even though I'm trying to regularize it to the best of my ability. So what I'm trying to highlight here is that there are some simple nonlinearities that can be used to ameliorate the prediction problem. So together, what I've told you about is that predictive processing of a visual signal can discover and exploit the symmetries that are implicitly at play in the data. Moreover, we've started from mathematical fundamentals and derived algorithms that can be used to model the nonlinear response properties of cells in the visual cortex. And can tell you more about this. And altogether, these methods remain very interpretable. It's just one layer, what I've shown you today, and one nonlinearity, and the performance is on par with complex architectures. So there are many natural extensions that I'm working on and happy to tell you about. One of them is stochasticity, so making predictions beyond the mean and taking into account noise and uncertainty. Another one is stacking this architecture. So following on what Bruno was telling you, you could do a scattering-like version of this model, and it gives interesting results. More importantly, I think, is the idea of tackling the non-commutative transformations. So it's a well-known result in representation theory, and I'm still trying to learn more about that field myself. But it turns out that the non-commutative groups cannot be diagonalized with eigenspaces that are 2-dimensional. You need more, right? And so what I'm trying to do is to learn this from data, and I'd be very interested in talking more with anyone who is interested in that topic. So with that, I'd like to thank you and take more questions.
Very interesting talk. Any question for Pierre? I have a question. So yeah, it seems like the method that you presented, if I understand correctly, it works for kind of like smooth motion, like if I'm understanding correctly. That's why the non-commutative group may comes in place. But if we go on internet, we find like a random video that they don't necessarily have smoothness in terms of motion. Like, have you tested on those problems that if I like just a person just like flash in and out of like a video frame by frame, would that still work? Because like you're not just predicting like the difference and all that. And I don't know how that would work in like the linear interpolation or well, not interpolation, but the linear operation or quadratic operation may not work for those things that just appear. Like, imagine a ghost video that just pop out like for a frame. And like, how would this method handle that?
Yeah, thanks for your question. So the idea here is that we're leveraging the temporal continuity of natural signals. So in real life, most things stay, and sometimes they move. That's really what happens. You can always come up with artificial examples where something else is happening, and that method would like not handle appearing content very well. But that's the point. The idea is to put myself in the position of the early visual system and considering the kind of input that you do get by walking around in the world. Can you try and predict those and leverage the temporal smoothness of these kinds of signals? There's another point that you made, which is that sometimes maybe you were thinking about occlusions. So there are transformations that are not really acting as groups. There's content that's hiding behind an occluder. And what happens here at the boundary is quite discontinuous and challenging to handle for any computer vision technique, especially like the motion compensation. So here the idea is to discover the group that's at play underlying all of this. Really, here there is still a simple translation going on in the 3D space. The only thing is that you get to observe a 2D projection on the back of your retina. So the thought is you could still learn a representation that has coefficients that transform nicely, like you would expect from translation in the 3D space. And think of this as an inverse problem. So your measurement device is low rank, but you can still recover some of the natural transformations that are at play in that implicit space that you don't get to fully observe. And that's possible because you get to see several successive frames. If you only saw one occlusion, it's very hard to tell where are the occlusion boundaries. So that's to say, the signals of interest are typically very smooth, but still there are some difficulties here. And those are actually the interesting bits. Perceptually, those are the places where we get a lot of information about motion parallax, about the depth plane and the distance of the objects from the observer. So these are actually really critical pieces of information from the point of view of an organism. So that's why I'm trying to understand them with this idea of inferring the transformation. Yeah.
I think it's in the line of this question. Like how far can you go in time? So you were always predicting the next snapshot, but like, is your technique making much better than CNN, or I don't know, predicting 10 snapshots away or something like this?
Yeah, so that's of interest, being able to see further in the future. And especially if you think about doing this in a hierarchy, maybe you want to predict further out coarser feature. I'm not sure predicting the exact pixel values is of direct interest to the organism. Here, what I'm proposing is that the visual system can tune itself online to learn good features by just observing the world that's happening, and then use those features to do other things, everything else that we do with our visual system. And the idea is that there's already a lot of information in next step prediction. What might happen, though, is that we might remember more of the past and this way handle acceleration. So you can rerun everything, including a bit more memory, and get better MSE results. And I'm trying to now connect this to what we are actually doing as visual observers and try to compare the performance of those methods with human observers. But yeah, about predicting pixels far in the future, I think that might be of interest for
or just
machine vision.
extrapolation, even like when the car moves, you even though you're on your bike and you're not yet there, but you somehow already you know the car is gonna not gonna be able to pass next to it, for instance.
Yeah, I agree with you. So I think the way I'm trying to approach this is by doing it at a higher level of abstraction. So this was the first layer, but I've cascaded this architecture, and you can do predictions further out in time on like features that are more abstracted, those that are more stable, because it's a lot of work to try and predict every single pixel, while they might not all be really relevant. You said the car, so we want to identify objects. So typically objects, they are coherent because they move together. So there is this theory that has to do with like the fact that objects are the thing that move together. This goes back to the Gestalt principle of common fate. So I think the structure of the phase advance here is a way to operationalize that idea of like objects moving together.
One last question. Oh, actually, we can do two. Yeah, please.
So there are a few that are really interesting, and they're slightly challenging. So let me give you one. Rotation in 3D. So it's not commutative, and we already know it's irreps. So the irreps are these eigenvectors of a transformation. What I told you about is for the commutative groups, all the irreps are one-dimensional, meaning a real part and an imaginary part. For this 3 rotation, the irreps are of dimension 1, 3, 5, 7, and so on. Right? So that's why it was critical to relax the pairedness constraint of the prediction mechanism that I've shown you. And I'm currently running these experiments, trying to get the results on a clear non-commutative group. And I'll show you the results later when I have them.
One last question from the back.
So So my question is about 3D rotation. Can you actually handle it? I mean, it's pretty obvious you can predict what happens on the borders because we miss information about 3D structure, but still, maybe we can predict what happens in the middle and recognize these transformations. Maybe you have like similar.
Please use your seat microphone.
Is it working? This way? I'm not sure it's working.
Pressed it. I hope you can hear me now. So it would be nice if you could show or like describe the picture you showed for 2D and translational latent spaces. How does it look like for 3D? And is it possible at all to do it?
Yes, it goes back to the question about even though the translation is happening in 3D space, your measurement device only gets a 2D projection thereof. Right? So there is a lossy linear operator in here, it's low rank, and so you sort of need extra information to infer what's happening in the implicit larger space that you don't observe. Because the transformation in the projected plane is complicated, and in the original space, it's much simpler. So the idea is to use the temporal continuity, the multiple views. Let's say you're a moving observer, you get to see this ball that's turning, but it's moving and you're moving. So there is a lot of redundancy in that spatial signal that you can exploit. So I don't have a full result for that, but that's the direction that I'm interested in working in. So thanks for your question.